Yes, you're excited to be back. Okay, today is 4-3. This is an indicator for what we call April, which, as you know, means snow because because you choose to live in Madison. So it's a choice. Um, so anyway, congratulations. Okay, so welcome back. We're going to remember this class is only really divided into three parts. We talked about virtualization a great deal. We talked about concurrency, probably the intellectually most difficult thing for us to get our heads around, concurrent programming. And we'll still do some work along those lines, which I'll talk about later. But now we're going to switch to the last of these three topics, right? So we've kind of done these two conceptually at least. And we're going to talk about the third piece, which is persistence, which you could think about really being like relating to input, output more generally. But it also has, we focus on persistence specifically because the storage of data on persistent devices like hard drives or flash-based SSDs is probably the most challenging part of dealing with I/O devices. It turns out to be an interesting subspace of how to build an operating system correctly. And so that'll be our focus is on really, instead of just focusing on input-output devices, really we're going to focus on disks and SSDs and the software in the OS above them, not SOW. That relates to them, which normally we call a file system. So that'll be part of the OS, and we'll talk about that in some great detail, and that's the last thing we're doing in class. So that's pretty exciting. Yeah, right. Ooh, yeah. It's been a long time, but there's still one more thing we have to make sure we do, which is we have to focus and make sure we learn this part as well as we learned the other parts so that we get a good full understanding of just the beginning of understanding computer systems in a deeper way. Right? Systems are very complex. Like if you go off in the real world and you're working, you will deal with systems that have millions of lines of code in them. And just understanding the OS gives you like a foothold into that, but it doesn't give you everything, right? In fact, what you begin to see as you understand a little bit about the OS is how much you don't know about how really everything works. But hopefully some of the conceptual underpinnings will serve you well as you go forward in whatever you do. Okay, so specifically then, what we're going to do today is we'll do a couple different pieces. We'll start just at the lowest level, which will start with devices more generically. Talk about that a little bit, and then we'll talk about hard drives specifically, or hard disk drives. Sometimes people call them HDDs, but we'll probably just say disk drive. So when I say a disk, I'll usually mean just a hard drive. This is a rotating mechanical creature. It still is commonly used in some parts of computer systems. So in data centers, inside of places like YouTube, storing all your Gmails. Eventually, those end up on some hard drive somewhere instead of something like a faster, more modern flash-based SSD. Why is that? Why do we still use hard drives when we have these newer technologies? Yeah. Wear out kind of relates to it, yeah. Yeah, cost, right? Cost and wear out relates to that, but absolutely cost is still a dominant factor, and the cost of hard drives is still a great deal lower than the other alternatives we have. And as long as that remains true, hard drives will exist. They've existed for 50 years. It's actually longer than that, 60 plus years, since the 1950s. And will they be around in 50 years from now? Well, who knows what's going to be around in 50 years from now. But if the world still exists and all that sort of thing, will they still be around? Maybe, maybe not, right? As people are pretty good at making there's enough of, we'll talk about why this is, but there's enough industry interest in these newer technologies that may eventually supplant hard drives. But certainly for the next 5-10 years, they'll be around, so they're worth understanding. And a lot of interesting history relates to them, too. So this is today. We'll talk about devices. We'll talk about hard drives. And then we'll talk about one specific thing that relates to hard drives, which it's a fun little part of class where we'll talk about I/O scheduling. So we've talked about scheduling before in the context of processors, right? CPU-based jobs. We've talked about scheduling and all those things you know and are find very endearing to you these days, like shortest job first and other sorts of scheduling disciplines. We'll talk about all those things today again, but instead of in the context of CPU-based jobs, we'll talk about them in the context of the jobs that are given to, say, a hard drive, which is little read and write requests, and how we schedule those, and what kind of techniques we use to do that sort of scheduling. So that'll be today. Somewhere in there, we'll do a break. And so I'm going to, for various reasons, it makes sense to present all this stuff together, so I'm just going to focus on kind of lecture material today. But we will, at the break, talk about the next project, which is about to be released, and we'll talk about the midterm, too, a little bit, which, well, I'll just give more information at the break about those things. All right, so good. Let's go forward then. Okay, so what we're going to start with is we're going to start with a little bit of devices and understanding. Really what we're trying to do is broaden our picture. Yeah. Is something irritating?
Yeah, your mic keeps cutting out.
Oh, okay. Feedback? And your feedback is that kind of sucks. Okay. This sounds weird. How about I just do this a lot? Does that sound good? I think I know why. It sounds really good, I think. Do people like this? No. Yeah, I don't know what's going on. I think it's called not working. Okay, 1 second. Yeah, this one needs a new battery, but I'll just do that. Lots of battery problems in here. Does any double E's have a theory as to what's going on? Yeah. To the pen, but see, I've been doing that all semester long. So, like, why would that be happening now? Yeah, I agree. I was thinking it's something here that I'm causing, but turn it off and on. Okay, computer science solution. Reboot it. That will probably work. Should I shut down the computer? Just try it all. I mean, it's funny. That's what you'll get out of your degree in the end. You'll be like, what did you learn? Well, if stuff doesn't work, restart. Yeah. What other things have you learned as an undergrad or grad student here, other than reboot? Any other lessons? OS? Oh, that's just operating systems. Okay. All right, let's try this one. Maybe it's me. Maybe I'm becoming radioactive. Maybe this is the beginning of like a superhero movie. Would that be awesome? How does this sound? Better? I appreciate that you were annoyed enough to say something, because I could tell it sounded a little bit funny, but not quite. So I would have just gone ahead blithely while you all just left the room. Okay, so anyway, back into this world a little bit. Sorry for the technical difficulty. I'm sure I'll edit that out later of the YouTube video. So what we've been focused on before we got to devices, of course, is really what we've been focused on are two components, right? We have a CPU, and it's connected to some kind of memory. And almost everything that we've been focused on kind of relates to that central part of a computing system, right? We have instructions and data in memory, and we have a CPU that's accessing them, and we figured out all these techniques to virtualize that. And then, of course, we figured out these even more interesting techniques to build multi-threaded programs and all the work that takes. But really, you could think of all those things focusing really just on CPU and memory. And of course, virtualization, we talked about virtualizing these two things, and concurrency just relates to processing and the model of memory that a concurrent program has. But of course, we all know that devices or other parts of a computer system are important for many reasons. And so we'll generally call those things that are not basically memory that the CPU is dealing with. We'll call those devices. And of course, there are many types of devices. What are some examples? Okay, nobody wants to say this is a silly question. Yeah. Yeah, you've been paying attention. A hard drive or a HDD, yes. A hard drive is absolutely a good example of a device. And an SSD we already talked about. What else? Yeah, NAND? NAND storage, okay. Like, so other types of storage, okay. Just NAND is also a gate. It's also like a kind of a geek way to use another, conjunction, so I didn't know what you were getting at. But yes, other types of storage. NAND, NOR, I didn't know what you were getting at. Yeah. Oh, yeah, sure. Keyboard, mouse, all these things. What else? What are other important ones? Yeah, like graphics, right? We want to be able to see things, apparently, on a screen. What else? Yeah. Sound, sure. Uh, yeah. An RGB light. Okay, that's right. This is actually what's interesting that you bring that up. This is actually the focus of our study. So most of the rest of the class will be on RGB lights. Um, apparently, we have like a drug user up here. Okay, so yeah, all sorts of USB devices. So sure. And then what's actually the biggest category that we haven't talked about? Oh yeah, networking, right? There's this whole thing of like this thing called the internet. It's amazing. And once you use it, you'll agree with me. So all these things are devices that you connect somehow to this basic system, and you turn it into what we call a real modern computer system. So the question that we're going to focus on then is, well, how do we connect devices to a system? And then we're going to focus on what's the kind of general protocol we have in interacting with them. Now, for each of these devices, there's a different specific set of ways of doing that, but we'll talk about some generalities and kind of go forward from there. If we think about it from this picture standpoint, well, let me just continue down here. CPU and memory. There's a lot of, how we used to draw this in the old times is we used to have what we'd call some sort of memory bus that would connect CPU and memory, some sort of relatively high-speed interconnect. And then hanging off of there, we'd have some kind of main I/O bus, maybe in the old, kind of a classic PCI bus. And then we might attach, we used to in the old times, maybe connect some devices directly to this I/O bus. And then we'd attached other slower buses off of that I/O bus, like for example, an old hard drive bus that people would commonly use is called SCSI, Small Computer Systems Interconnect. This is a hard drive. And this was kind of how we conceptually looked at systems. It's evolved a little bit. So if you look at a modern system, sorry, let me leave that up for a second. A modern system has all these same interconnections here, but they just kind of structure a little bit differently. So if you look at a modern example from, why don't I just look it up instead of talking about it. So let's say we looked up Intel, I wrote one of these down. Let's see if this is a good one. Let's see if we can get a diagram here. I should have looked up the exact web page instead of randomly doing web searches in front of you. How about we look for images? Yeah, so here we go. This is at the very reputable hothardware.com, a site we all visit for our latest, hottest hardware news. But you can see here yeah, I never saw that before. So you can see here there's something actually very similar about the diagram, but it's something also different. You see the processor is here. You see that here, over to the right side, we have some sort of high-performance connection to memory and a specific type of memory. And then what you see here is that because over time graphics became something that had to become incredibly high performance means we need high bandwidth channels from, say, processor and memory to graphics. That became connected very close up to the processor itself. Then below, to connect all the other types of devices that you want to the system, you can see Intel's made this specific chipsets over the years. And attached to there are all the different types of devices that you're used to, like PCI buses, SATA instead of SCSI, SATA is a common hard drive interconnect, USB, et cetera, et cetera. So looks kind of the same, but it's a little bit more organized through specific chips that come out of Intel that serve essentially as a main I/O controller. The details of all these things, we're not going to get into too many of the details, but again, we're going to talk about it just at a high level, the types of things that we need to worry about when we're thinking about I/O. So that's that piece. I just wanted to show that really quickly. So I'll just write down there example Intel and Z270 chipset. And again, see hothardware.com. Yes, I'm writing that down. Site you didn't know existed. So the whole point is there's a bunch of devices and we need to interact with them. Now, the question is, when I kind of drew these things before, with a memory bus that is connected to memory and then like some sort of generic I/O bus and then some sort of SCSI or maybe SATA interconnect, it's kind of arranged in a hierarchy in systems. And you can see that hierarchy even in the modern systems with high performance connections to certain types of things. Why do we have this hierarchy? Why don't we just plug everything into the CPU and make it so we can access them all equally effectively and with the same kind of high performance? Why do we have arranged things? So like, for example, these buses down here, like a SATA bus is generally, lower performance, but why do we do that? Why don't we just plug disks into the memory bus, for example? Yeah. Well, I think you're getting at the general answer, which is it relates to cost as well. We want to build the most cost-effective system. And if we have devices, if we think about the rates of these devices, like memory, you think about it being in many gigabytes per second, many, many gigabytes per second these days. Hard drives, you might think of as being something like, in the best case, 100 megabytes per second. Or if you're using them, poorly, we'll talk about that today, maybe 1 megabyte per second. So attaching slow devices onto a very high-performance interconnect doesn't make any sense, and it's also very expensive and very hard to do. It's hard to make a very high-performance interconnect, especially one that can attach a lot of different devices. So just kind of from a double E standpoint, we want to, and just from a cost performance standpoint, we want to build a system that we need, not just one that could be kind of infinitely good at whatever cost. So cost is a reason we think about all these different sorts of layers and hierarchies in these systems. But logically, we can just access all these devices from the CPU in kind of the same way. It just means we have different, the instructions that access memory are, of course, going to be different than ones that send things to the network, then send things to the hard drive. But there's a lot of similarity in there, too, and we'll talk about that. Okay, so let's talk about then the interface, like a device interface in a generic sense. So any one of these things is a device, a network card, a hard drive, whatever. And all of them at some point have an interface that they're presenting to the CPU. And that needs to be something that the CPU can access in order to get the device to do something for it. And so we'll have a generic kind of interface that we'll think of. So, and we'll think of that interface as being embedded in what we'll call a device controller. You can think of that as just hardware that presents the interface of the device, presents the interface, and it, of course, implements the device functions. And logically, each device is, of course, quite different, but we'll think of it as having a few different standard parts of its interface. So we'll have some kind of, say, registers that the CPU can interact with in order to get the device to do something. And we'll think of a few different types. First, we'll have like a data register, perhaps, where we might move data in it, like write data to or read data from in order to do either give information to the device or get information out of it. We'll have some sort of command register where we can put a specific command. Like if it's a hard drive, you might have a read command or a write command, or perhaps like a flush command. We'll talk about why that might be useful in a hard drive context. And then we might have some sort of status register. The status register will tell us what's going on with the device right now. Is it busy or is it not? Is there an error from the command that we just issued, etc. So this is at the lowest level. And what we're going to do now is just develop a little protocol of how we interact with this device. Then we'll see some problems with that protocol and try to make it a little bit better. And we'll take a quick break and then start talking about hard drives in some detail. And of course, this is just the interface part of the device, right? This is the interface. Maybe I should do that in a different color. This part is the interface. But of course, the device isn't just an interface. It has whatever its internals are. And very simple devices, that'll be a very specific set of chips that implement whatever the device needs to do, like a network card has certain kind of ring buffers that you put messages into or get messages off of. Then has connections to all the low-level things it needs to do to send messages out over whatever kind of network it is, whether it's like an optical network or just a typical wired network. A hard drive controller has to know lots of details about how a hard drive works. And the more complex the device gets, the more likely it might have, for example, some kind of microcontroller inside of it, and things like memory. And pretty soon, the more complex is, we'll see this in some examples next time actually, as we get to even more complex devices. Inside of a device is a CPU, a bunch of memory, a low-level programming environment, and it really looks like a computer system. It's just a computer system dedicated to doing the activity of this device as opposed to doing some sort of general purpose thing. So it can be pretty complex in the internals. For now, we'll just kind of assume it, whatever, we'll have a generic view of it. So let's talk about this generic protocol for accessing a device. We'll see some problems with it pretty quickly, but let's just go ahead and do that. So the first thing we'll say is while, say, the status of the device is equal to, say, busy. So the first thing we're going to do is check if the device is available for us to use, or is there something already else going on with the device. And what we'll do at that point is just kind of spin and wait for the device to become free. Then what we'll do is after the device becomes free, what we will do is we will then figure out how to give it a command. And so we'll do that by basically saying writing some data to the data register. To maybe we want to, let's say, write some data to a device. So we're put some data in this data register first. Then we might say, well, what's the specific command? Well, we'll write a command to the command register. And once we write a command to the command register, the hardware will know, oh, the data that I need is already there, so good. Then I've gotten this command, now I know I need to do something with this data and this command. And so then the device, at this point, can begin operation for this command. And then what we would like to do at the end point is basically maybe wait for the operation to be done. So for example, if you issue a read to a hard drive, you want to, of course, initiate the read, but you also want to then wait until the read is done, because then you can get the data back and kind of continue your program onto the next thing that it's doing. So again, at the end, to wait for completion, we'll kind of do the same thing. We'll say while status is equal to busy, just spin. Another form of waiting. So this is identical to this, right? Okay, so we have our device. It has an interface. The CPU up here, right, in our diagram. The CPU somehow it gives data and commands to these registers that are in each device. Then the device takes those commands, like say a single command at a time, let's say, and then works on it for a while, and then eventually gives you back maybe some kind of answer, like what the status is, success or something like that. Okay, so now we're going to talk about some problems with this, or maybe some, let's call them questions that we might have about this. First, it seems like there's some inefficiencies with this. Oops, inefficiencies. That's right. What looks inefficient about this? What looks bad? Yeah. Yeah. Anytime you see spin waiting, you say, I'm spending a lot of CPU time waiting for a device. I'm just sitting there basically accessing a register over and over again on the device. In some cases, that would make sense. When would that make sense? What kind of device might that make sense for? Yeah. Yeah, something that's super fast, right? Like you have a new, like you were saying, NAND storage device, something that's a very high performance storage device. Maybe it's going to get back to you right away. So if you spin, you'll just spin for a very brief amount of time. If it's a hard drive, how long does a hard drive take for a particular request? Just approximately. 6 milliseconds. I love it. Yes, that's exactly right. That's a good answer. So it's, yeah, about 6, 10, 20 milliseconds. And of course, if there's many requests queued up, it'll take longer than that. But on tens of milliseconds. If you're wasting CPU time for 10 milliseconds, how many millions of instructions could you have issued in the time that you were doing that? Many millions. So clearly that's not such a great idea. So one inefficiency is clearly this sort of spin waiting. So we'll talk about a way to get around that. Early devices didn't have those ways, but then people soon enough figured out ways to get around that. What's another inefficiency? Yeah, or did you have a different question? Oh, sure. So you're talking about like error handling? Yeah, that's an excellent point actually. We're basically right now we're kind of ignoring this, and I will mostly ignore that for now. You're right that a modern interaction with a device has to be very conscious of error handling. So for example, if the device, something goes wrong with it, you have to have ways to back out of the protocol and then maybe do a different series of things in order to try to get things going again. Of course, what's the first thing you do when the device isn't working? You try to reboot it. You essentially send a reset to the device and to get it to try to reset itself and then get going again. And then, of course, at some point, you'll just report an error and say the device that no longer works. How many people have had like a hard drive or some device fail in their computer? Yeah. How many of you have lost data as a result of that? A few of you. It's a sad story, right? So you should always back up your data. That's the lesson. You learn that lesson at some point in your life, right? That you should always back things up. It's a sad but true story. We'll talk about that too later. So that's true. This is an excellent point, but I'm mostly going to ignore that. It's true that a more realistic protocol needs to handle that. It's a nice observation. What else is inefficient about this? What if we're, one thing you might notice here is when we're sending like data to the device, what we're doing is the CPU has to do that itself. It's like essentially writing data into this register 1 byte at a time or 4 bytes at a time. That works fine for small bits of data. If you're sending a large amount of data to a hard drive, for example, let's say you're sending a 1 megabyte write request to it, the CPU has to spend a lot of time transferring that data itself. That also turns out to be inefficient because what that's doing, sorry, is just doing essentially a copy. Like it's taking data from here, reading into the CPU, and then say maybe writing it to the network. And then it's getting the next 4 bytes, reading them in here, writing them here. It's a very expensive copy that the CPU has to spend a lot of time on itself. And so that data movement is something that people have focused on and figured out how to do more efficiently with less CPU involvement. Because again, if we free the CPU can do other more useful work, like for example, actually just doing computation of whatever a given process wants to do. So those are some inefficiencies. And then there's a little bit of question of how to basically do I/O, which we'll just briefly answer. Because when we were talking about writing data to a data register or a command or reading a status register, we haven't really said anything about how we do that. So we'll just briefly touch on, basically how to read and write registers on the device. So that's something that we will briefly discuss. So we'll just talk about these, and then we'll take a little break, and then we'll get into hard drives in some gory detail. So let's think about first the spin waiting problem. So let's particularly just focus on the second one. That's kind of perhaps more interesting, but it applies to really both cases. So the interaction we have here is a pretty simple one. We're constantly just reading this register, and we're waiting for it to change. And when it changes, we know something has happened in the system. So that seems fine, but it seems like we want to, how to maybe avoid that. What we want to do is avoid CPU waste, especially for slow devices, like we said. And the idea, of course, here that we have is that we want some more hardware mechanism here. And we already know what this mechanism is. The mechanism is what? Yeah, an interrupt, right? Interrupts, when they were first introduced into computer systems, amazingly, if you go back far enough into like some of the historical discussions of these things, were viewed somewhat controversially. Like, hey, why would we do that? That seems like it's really going to mess up. We're making it so an interrupt might happen at any time, and we need to be able to handle it. I don't know if we'll be able to build a correct computer system that has this thing that the device, might interrupt you. Speaking of interruption. That's me calling you. So don't interrupt me. So, so in any case, yeah, it was a little bit controversial because people had this notion that it seems complex. Well, sometimes the device might get back to you really quickly. Sometimes it might get back to you very far in the future. It's a variable amount of time. Can we really build a correct computer system? And then what the nervousness was there, or the anxiety, was really related to, I think, people beginning to sense that this was making the computer into a much more complex concurrent system, that there could be lots of things going on at once. So for example, we have our CPU and we have our device here, and we know that if we're like, hey, we're running along issuing instructions, but then we tell the device to go do something, and the device is going to go ahead and do it, and then when it's done, it's going to, say, interrupt us. And then we can kind of keep doing what we're doing. And of course, in the meanwhile, what we have is this opportunity to do something else. Right? This kind of overlap is central to what we've been talking about when we talked even about the early days of multi-programming and just having multiple processes in a system. And when one is waiting for something slow, you switch to something else. That's the efficiency we can gain here. But it does mean we need to be able to kind of deal with this and make sure that when we handle interrupts, we handle them correctly. That was kind of the concern. But of course, pretty quickly people realized it's possible to build a fundamentally sound system even with something that happens with variable timing. And so the interrupts are exactly that mechanism. Now, we've already talked about this in the context really of a timer interrupt, but of course all the same kind of basic notions apply here, which is a device that has interrupts as a way of kind of interacting with it. Sure, we program it to go do something, then we can go do something else, and then when it goes ahead and is finished, it'll raise an interrupt line to the CPU. The CPU then will change what it's doing to run. Instead of run the code that it was running before, it'll essentially run an interrupt handler, which we've seen in xe6, for example, which is just like any other sort of exceptional thing going on. It's just some code we need to run, say, in the operating system in order to handle what is going on here. Like, this disk request is complete, and now we can continue working. So if you're thinking about that a little, let's pretend this is a hard drive again, an HDD. We can think of it more like what's happening here, of course, is on our CPU, we're running along, and then we say issue a read system call. That read system call goes through the file system in the operating system, which we'll talk about more later, how that works. The file system actually then goes down to a lower level piece of software, which we'll talk about a little bit too, called a device driver. You can think of this as being the kind of the low level way of interacting with a device. The device driver eventually knows for this specific type of device how to issue commands to it. And then eventually, at the lowest level, this will be able to issue the I/O command. So issue whatever the low-level I/O command is. And then at that point, say the disk that we're talking about, the disk will start working on that request. Now, what are we going to do to the process that was running and issued the read request in the meanwhile? What are we going to do with it? Given this is the OS class, what are the things OSs can do to a running process? Yeah, it's going to become blocked, right? So it becomes blocked or sleeps on I/O. You can see why when Dijkstra was building some of the very earliest operating systems, why pretty soon he and his colleagues invented a semaphore, because one of the things they needed to do was to wait on a condition to change, namely, is this device request finished or not? And then later, when the interrupt occurs, of course, what happens is this device is done, and what it's going to do is call into some sort of interrupt handler, and what that interrupt handler is going to do is unblock the process, right? And perhaps put some data somewhere, etc. And then we can continue running again. So when we're issuing something like a read or any sort of system call that's interacting with a device that maybe has a long latency and has this kind of interrupt-based mechanism, we're likely going to put the calling process to sleep. Then the device is going to do its thing. In the meanwhile, the OS could switch in this time here and run something else. So we could, for example, in this time, run some other process, run, process 2 or whatever. And this was process 1. And then finally when the read is complete, we're going to unblock that process, change its state from blocked on an I/O back to runnable, maybe just start running it right again, and then continue from there. And you can see how much more efficient we're being then in terms of utilization. We're using the CPU the whole time to run something. As long as we have something to run, it's a better use of the CPU than just spinning there for however long. Okay, so that's kind of a generic, why we want to have interrupts in systems other than the timer interrupt, which we've talked about for a mechanism needed for CPU virtualization. Just a general thing we need in systems when we want to be able to deal with devices that have all sorts of different latencies, especially when they have variable latencies. You don't even know how long it's going to take for them to finish. It makes sense for the device to tell you instead of polling it repeatedly, right? So spin waiting, yes, I should also say sometimes just called polling the device. Okay, any questions about that? That makes sense? Okay, so really quickly then, another piece of this interaction, let's draw the same timeline. Again, this is all these diagrams are time going this way. We have our CPU, we have, say, our disk again. Let's say we want to write some data to the CPU, from the CPU to the disk. So we're going along and then we call write. We want to write some data to our hard drive. And again, that would go into the file system and whatever, eventually go down to, say, the I/O layer or I/O device driver. And what that would eventually do is start copying data from the buffer that the user passed in down to the device, whatever it's through its data register, right? So just kind of writing data. So it's copying data from, say, a CPU register or really from memory through the CPU back down to the device. And this could take a long time, right? If you're doing a very large I/O request, this part could take a long time. And it's just essentially a very inefficient thing for a CPU to be doing, right? The CPU, we want it to be executing instructions up here. We want it to be executing as many user instructions as possible, not just copying data from some location in memory down to a device or vice versa. So pretty soon when people were building systems that were doing this a lot, they realized they were spending a lot of time in this kind of copying part of this protocol. And they thought, why don't we basically reduce the CPU burden by using a burden with more hardware, essentially, more specialized hardware. And in particular, they invented something that's essentially called direct. It's not a really great name. You could call it a copy engine, but it's called direct memory access, or DMA. And what DMA is going to let you do is basically let the CPU tell some device, basically get some assistance from the device world in order to do the copy directly from memory to the device or vice versa without the CPU being involved, as you can see from this really clear diagram. This, by the way, will be on the exam final. What is the importance of this line? So what I'm trying to show you is if you're in a traditional path, let's say without DMA, data travels like this. Let's say down to this hard drive. That's too hard to see, isn't it? Okay, let me do it differently. It's green. You can't see any of this. All right. How about I have a better idea? When you don't begin well, begin again. CPU, memory, and then device. This is our canonical system, made as simple as possible. here's our without DMA path. Let's use green. Without DMA, we like read from memory into the CPU and then say write down to the device. So this is without DMA. With DMA, what we do is we program the device. Let's say we tell the device what it needs to do, and then what it'll do is just transfer the data directly. So this is program, and then this is actually do the transfer with DMA. So it's a pretty simple idea. It's basically a little engine that's a copying engine that can move data from devices to memory or vice versa. Now you can imagine some complexities there. When we think about memory virtualization and devices, why do we have to start to worry a little bit about that and using direct memory access? What kind of things could happen while a device is transferring some data from a device to memory? You're really worried about these device crashes. Yeah, no, it's not. I'm not talking about device crashes. What kind of normal OS kind of thing could happen that would maybe be bad if the device we're running and it was transferring this, doing this direct transfer from, let's say the device had some data that we were interested in. It was transferring data to memory. It was taking some time because it's not an instantaneous operation. And then the OS, who's normally in charge of of memory and who owns which page? Well, not too many answers to what's the name of this class. OS, right? The OS. It's often an answer. It's a good guess. So the OS is in charge of who owns which page, right? Like, for example, process 1 owns this page, process 2 owns this page, and maybe the process that issued the I/O, this is where we're trying to transfer its data into that page. What kind of thing could happen that we might be worried about that the OS might decide during this transfer? Yeah. Yeah, it might do some memory management. It might decide to swap, like, that page no longer needs to be in memory. It might decide to reorganize memory. It might do any sort of thing that makes that page no longer the page that it used to be. So what does that mean what the OS needs to do when it issues, before it issues like a DMA command to a device? What does it need to make sure of is true during that transfer? Yeah. Yeah, that nothing changes about this state of the system. So there's some OS work involved here. We're not going to talk about it in a lot of detail, but you can imagine what the OS is doing is making sure that this page stays here. Sometimes people call it, sorry, I don't know what that is. Sometimes people call it technical difficulty there. This page is say, pinned in memory, which means it can't be swapped out or given to some other process. We first pin it in memory, then we tell the device it's okay to do, say, a DMA into it, then we let the device go and do that, and then when it's done, we kind of unpin it and make it part of the normal, part of our virtual memory management again. Just some details there, not super important, but you can imagine that's the type of thing you need to think about in the bowels of the OS when it's doing things like this. So that's the generic benefit of DNA, and instead of spending all this time copying data, the CPU is now freed from it. It just tells the device, here's a start, here's a length, it describes basically a buffer that needs to be moved, says which direction it is, it then says go, and that specialized computing engine inside the device then does the work of the data movement for you. So that gives us a high-level answer onto how do we avoid the inefficiencies of spin, waiting, and data movement. There's just one last question I'll answer, and then we'll take a break, which is how do we actually interact with any of these devices, including the DMA engine? So let's just answer that down here. How to interact with a device. And traditionally, there's two types of ways we do. We'll see some examples, really mostly on x86, of I/O instructions. So specific instructions provided by the hardware in order to allow you to access those, say, registers. That certainly exists, and we'll look at some of those in x86 later on. So there's certainly examples of this in x86 generically. And those just take, like you might expect, they take like some kind of address which lets you refer to different devices, and then whatever other information you need to pass to the device. So that on x86 these are the in and out instructions, and we'll look at some of those at some point. A different way of doing it is what we call memory mapped instructions, memory mapped I/O. That basically, instead of having specific instructions, what we do is the hardware maps those registers. So we talk about our device registers as kind of an interface. The hardware maps those registers into some part of the memory space of the computer system, and then you just read and write essentially memory. And what the hardware then does is turn those into writes or reads to the devices themselves. So that's something called memory mapped I/O. It's just a kind of a slightly more modern way to interact, and you don't have to then have special I/O instructions. You can just use normal loads and stores to deal with the devices. So a lot of details to that. We're not going to talk about any of them. It's just some phrases that you might hear about I/O instructions or memory mapped I/O. Those are all both just ways of talking about how do you talk to the device more specifically. And all these things are better learned by specific examples, so we'll look at some of those later on, but not today. Okay, so that's a very high-level overview of devices and how we interact with devices and how we do so efficiently. Let's take a break, and then we'll talk about a specific device when we get back. Our favorite hard drive.